Hello everyone, I'm Ahmet Can Sayimlar. Today I'll be presenting my comparative study on page replacement algorithms. Basically, I'm going to talk about why old methods like LRU aren't enough for modern computers anymore, and how smart algorithms like ARC solves today's performance problems. So, why does this topic matter? As you know, processors are getting faster every day, but storage speed, like our hard drives, isn't keeping up. This creates a huge I/O gap. When our RAM is full, the system has to decide which page to kick out or evict. If the algorithm makes a bad decision, the CPU wastes time waiting for the disk. We call this trashing, and it kills system's performance. Let's quickly review the basics. First, we have OPT, the optimal algorithm. It's theoretical because it's not the future, so we just use it for comparison. And there is LRU, least recently used. It assumes that if I use a page recently, I'll use it again. It's good, but it has a major weakness: scan intolerance. If you copy a large file, LRU fills the cache with that file and deletes your important data. I want to highlight a strange behavior in the FIFO algorithm called Bilaty's anomaly. Normally, you'd expect that adding more RAM frames would reduce errors, right? But look at this example. With 3 frames, we get 9 page faults. But when we upgrade to 4 frames, the faults actually increase to 10. This proves that simple algorithms like FIFO can be very unstable. Now, let's look at modern solutions. First up is LIRS. As I mentioned, standard LRU fails when you scan a large file. LIRS solves this by using a metric called IRR. It separates pages into 2 groups: hot LIR and cold HIR. The smart part is that one-time scans stay in the cold buffer and are quickly evicted, so they never pollute your main cache. ARC, Adaptive Replacement Cache. This is the most important part of my study, the ARC algorithm. Unlike others, ARC tunes itself automatically. It splits the cache into 2 lists: L1 for recent items and L2 for frequent items. But here is the magic: it keeps ghost lists B1 and B2. This track the history of deleted pages. If a ghost page from recent list gets a hit, ARC moves this target parameter P to make L1 bigger. If a ghost page from the frequent list gets a hit, it makes L2 bigger. So it constantly adapts to whatever the computer is doing. So are these actually used in real life? Yes. This AFC file system uses ARC directly because it's scan resistant, which is critical for servers. Linux page cache. Linux cooling uses pure ARC due to patents, so it uses a similar approximation with active and inactive lists to get same results. Clock Pro approximates LIRS performance using low overhead circular structure with 3 clock hands, enabling high concurrency in OS kernels. Hardware is changing too. We now use SSDs and NVRAM. On these devices, writing data is much slower and more expensive than reading. That's why we have algorithms like CFLRU, a clean first LRU. It prefers to evict clean pages first and keeps the dirty pages in memory longer to save disk life and reduce latency. Finally, let's look at the numbers. We compared them using the standard SPC1 benchmark, which simulates a financial workload. Traditional LRU only achieved a 9% hit ratio, but ARC reached 20%. That is more than double the performance, which makes a huge difference in system speed. So, to wrap up, while LRU is simple, it's not enough for today's data-heavy tasks. Adaptive algorithms like ARC and LIRS are the current state of the art because they handle scans intelligently. In the future, we expect to see more hybrid approaches using machine learning. Thank you for listening.